and the recording has started.
Wonderful. Are we good to start?
Yep, for sure.
All right, wonderful. Thank you very much. So to confirm you can hear me well, just going to change my mic setting here.
Yeah, we can hear you.
Wonderful. All right. Thank you very much, Sahil. Thanks everyone for joining today. I'm really glad to get to speak with you all virtually, and hopefully in the near future I can speak with you in person as well. That would be really fun. I'm going to go ahead and share my screen here. First, just to start off, give you a little bit of background. My name is Tanmay Bakshi. As I mentioned, really excited to be here today. And today I want to talk to you about the world of what you might call artificial intelligence. I want to give you sort of a deep dive into some of the fun projects I've worked on, things that I think are really fascinating. From there, I want to sort of tell you about the misconceptions that revolve around the world of artificial intelligence and machine learning, and then how actually you can get started building your own machine learning technology as well, building your own applications that are powered by it, and so much more. Now, just to give you a little bit more context on who I am, really, I love working with the world of technology. I love building technology, solving problems with it, and especially helping more people use technology to solve problems as well. That's something that I've always been really passionate about. And to sort of give you some more context as to the journey that I've sort of taken to get here. I mean, I started coding back when I was 5 years old. My dad used to work as a computer programmer, and so watching him program was really fascinating. Computers really piqued my interest. So he saw that curiosity, helped introduce me to the world of programming and writing code. Of course, my curiosity just continued to grow. So I started to use, the internet and books as different learning resources. When I was 9, I had my first iOS application accepted to the Apple App Store. And from there, I also started to create YouTube tutorials to help more people learn about the world of technology and how they can build their own applications to solve the problems that they see or that they face, right? As a matter of fact, to date, I've also authored 4 books to help people learn different complex technology subjects, starting from all sorts of various starting points. Now, through this journey, there was one point that really stands out to me as when things sort of changed for me, how I viewed the world of technology really changed that day. And it was when I was 11. It was when I stumbled upon the world of IBM Watson and how it not only played, but also won the Jeopardy game show against the 2 best human competitors on the show. I mean, I'm pretty sure you've probably heard of this before, right? And to date, it is still one of my favorite applications of machine learning ever, because it's hard to fathom just how complicated this task was. And to think that we achieved this milestone in computing back in 2011 when machine learning was in its infancy. I mean, Jeopardy is insanely complex. Like, you've got clues that have all kinds of riddles and wordplay and puns and references, and to be able to understand that and to be able to relate it to quite literally tens of terabytes of text data that you've got stored, and to do so in 3 seconds it really amazes me, right? So I saw that and I was instantly like, I gotta know how that works so I can do this sort of thing myself as well. And so ever since then, I've been, fascinated by working with the world of machine learning and AI technology in a wide variety of different fields. Now, of course, there's the term artificial intelligence, right? That's sort of the classic term that everybody's heard of and everybody uses to refer to this technology. But if I'm being totally honest, in my opinion, I actually don't think artificial intelligence is an accurate term for a lot of, what fascinates us these days. I think artificial intelligence is more of a user experience term than it is a technology term. A lot of the things that we look at today and we're like, hey, that's artificial intelligence powering some kind of next generation user experience. Really, what's going on behind the scenes is machine learning technology, and in a lot of cases, specifically deep learning technology. Now, this might not seem like that much of a big deal, but I think it's a really important distinction, and I'll get back to why in just a few moments. As a matter of fact, if you take a look at a bunch of different companies, a bunch of different enterprises, right? Gartner actually held a survey and asked them what they think the most disruptive technology out there is today. And 72% of them voted machine learning technology. I mean, I knew I was fascinated by machine learning tech, but it's really interesting to see that even organizations, businesses agree with the fact that the vast majority of them say machine learning is the most disruptive technology out there. But why? Right? Why is that such a large number? Well, I think this quote puts it perfectly. It's because of the effect it can have on existing processes and the way people will work. All right. Now, I'm not going to tell you who said this just yet. I'll get back to that in a little bit. But just keep this quote in mind and remember this as one of the reasons as to why machine learning is so disruptive. And I'll get back to this. It does tie back in a pretty fun way. Now, to sort of dig a little bit deeper into this and to sort of explore a bit more as to why AI is so important, I think it's important to understand that technology isn't just its own domain or industry. Technology really is infrastructure, right? Technology acts as, the infrastructure for basically every other domain, right? I would be hard pressed to name an industry that is not reliant in today's society on some kind of modern technology. And this applies pretty much everywhere. You could take a look at the world of healthcare. Now we have all this advanced machinery, education, and especially during the pandemic, how, for example, we were able to switch everything to be virtual. Agriculture and how we can make things more efficient, how we can make things a lot quicker and a lot higher quality in the world of entertainment, how we can trade with people, halfway across the globe instantaneously with technology in the field of finance, right? Technology works everywhere. And here's the thing. Of all these different next generation technologies in the survey and ones that you've heard of, blockchain, cloud, IoT, AI, all of them, they apply to quite a few of these, but not necessarily all of them, right? Like cloud, maybe there's a lot less cloud involvement in agriculture because then you want to do more compute on the edge, right? Or maybe the entertainment industry doesn't really care about blockchain as much. Or maybe in education, IoT has less use cases than maybe it would in healthcare, right? But machine learning, or what you might call AI, is more universally applicable. You could apply it practically anywhere here. Any one of these domains, I could come up with a couple example use cases that genuinely have value to apply machine learning in. Right? New problems that we could have never solved before. And the reason for it is really simple. It's because at the end of the day, machine learning from a technical perspective really just boils down to very complicated data analysis that might not sound as attractive as, artificial intelligence, but at the end of the day, that's what powers that technology. That's what powers that user experience. And I've been able to do some pretty fun things with this data analysis capability. And I'd love to go ahead and show you a couple of these fun projects now. Again, things that I think are really fascinating. And I want to start off with one that's particularly interesting to me called Hard ID. As you may have been able to guess from the name of the project, the idea is basically to be able to identify people based off of the way that their heart beats, based off of their electrocardiogram, their ECG. Now, Heart ID works in a couple stages. Of course, there's development training, which is where I train neural networks, deep learning systems, to be able to identify unique features within heartbeats. And then there's production training, where I take new raw electrocardiogram and then process it through my deep learning algorithms in order to extract unique features. From there, I can take brand new electrocardiogram that I've never seen before and predict whether it matches the identity of somebody existing in the database. Now, of course, the way that this works is these neural networks that I've built extract, as I mentioned, unique identifying features from your heartbeat. So for example, if I were to go ahead and take heartbeat data from me and my sister, as you can see, the bar graphs on the right representing the unique features that the neural network extracts, they are different for both me and my sister because, well, we're different people. So we have different heartbeats. And the neural network was able to pick up on that, extract unique features that are different between the two of us. And these are actual features plotted out on a bar graph. And here's what I think is really fun. So a little while ago, one of my friends told me that her and her sister can actually unlock her phones with Face ID, each other's phones, actually. What does that mean? Well, let's just say you've got, sister A, her name is Simone, and she registers her face against iPhone Face ID. Well, her sister, Raquel, can actually unlock her other sister's phone without ever having been registered in the system. they can trick Apple's Face ID. I'd love to show you that right now really quickly. So here's Simone. She can unlock her own phone Face ID. Of course, it's her phone. Hands it over to Raquel. She can also unlock it. But handing it back over to Simone, going to settings, taking a look at the Face ID settings, there's only a single appearance setup. All right. When I saw this, I instantly thought, wouldn't it be really fun to see if Hard ID could recognize between them? So I spun up the algorithm, took a couple seconds of electrocardiogram data from Raquel. I was able to successfully identify her as, well, Raquel. And similarly, a couple seconds of data from Simone, and there we go. We can identify her as Simone. So I feel like this project's really fun, especially to be able to say that it works in some cases where even Apple's Face ID doesn't. So it's a really fascinating project to me to see the kinds of minute patterns that you can extract from data when you use these kinds of complex deep learning algorithms, right? As I mentioned, powering next generation user experiences, solving problems that you couldn't have solved before. But even though this is really fun, my real passion, I think, is in the world of language, right? I am really, really fascinated by applying deep learning techniques, AI, in the world of language and linguistic data. And the reason, the reason for that is because language affects the brain as much as the brain affects language, right? Quite literally, the language that you speak can determine the way you see the world. What do I mean by that? Well, some of you may have seen this example before, but if you are a native speaker of Russian, you are actually more likely to be able to determine the difference between more similar shades of the color blue. And that's just because there are more words for the color blue in the Russian language. And so you're more likely to be able to differentiate between them. So for example, if I were to show you these three shades of blue and ask you which one's different, you should mostly be able to tell that quite obviously B is the different shade of blue. You know, I could get a lot harder with this. I could give you more and more similar shades of blue across the three. So for example, across these three, take a second if you need to. Most of you can probably tell me that C is the different shade of blue. We could get even harder and harder. And in actual research settings, scientists were able to determine that with more similar shades of blue, Russians can more accurately tell the difference, right? So for example, in this case, we've got B. And in this case, a lot more similar, but sometimes screen share compression can make the difference a bit more noticeable. It would be A. Right. And so as I mentioned, language is really fascinating because it ties very, very deeply into natural intelligence. And so being able to simulate some linguistic capabilities in artificial intelligence almost gives, that illusion of natural intelligence itself. It's really fascinating, especially because the world of natural language is infinitely complex. You could even have totally syntactically valid sentences like colorless green ideas sleep furiously that really mean nothing, right? I could perfectly validly parse this into a syntax tree, but really this doesn't mean much of anything, right? And so this is why the world of language fascinates me. And the thing is, I've worked on a lot of different projects that use the power of AI with language. And as I've worked on them, as I've worked on more AI-powered projects, I've sort of noticed a couple of key misconceptions that people have about the world of machine learning. One of them being that we're trying to simulate human intelligence. And that sort of misconception is especially exacerbated by, for example, the representation of machine learning technology in humanoid robot form, right? A lot of people think machine learning is about simulating human intelligence. It's not. It's about pattern recognition. It's about finding patterns in unstructured and structured data at scale. Some people think it's about solely replacing human jobs. Once again, it's not. It's about taking certain kinds of, human decision-making capabilities and enabling computers to emulate them, to enable us to solve new problems. And at the same time, a lot of people also think it's about surpassing human intelligence and sometimes creativity. Again, that's not the case. Human intelligence works completely differently to how these algorithms work internally. And that is what I want to get a little bit deeper into now. You see, a little while ago, I saw a news article on artificial intelligence, and the title was, "Can Artificial Intelligence Replace Songwriters? Study on AI Lyrics Suggests It Is Possible." And when I saw this, it was sort of like a breaking point for me, because I had seen so many articles like this about artificial intelligence and machine learning and how it's replacing, creative professionals, from songwriters to journalists to developers writing code. And I wanted to create an example application that proves that no, AI is not here to replace these creative professionals, but also B, that it can be valuable for them to help them as a tool, right? And so I started working on a project called Lyricist, a project aiming to augment songwriters using the power of AI to help them effectively eliminate writer's block, right? Infinite lyrical suggestions at scale. And of course, it was a very difficult project to work on. I knew from the very beginning it was going to be a long and hard journey to build this. And some of the examples that I like to give as to why it's so complicated is, for example, looking at a simple verse like this one, for simple song lyrics, this is human written stuff. You can probably understand what it means pretty well, but even just understanding the second line in this verse needs a lot more context than you might imagine. Right? It needs you to understand the context of the song, how the line relates to other lines, what Tylenol is, that it's medication and that it helps you sleep, but that it's not working in this case, and what's the metaphorical meaning of it not working, and so on and so forth, and understanding that humans need sleep and that it's unhealthy not to get it. There's so much context that you can't just program, right? You can't symbolically link all of these things manually. You need a way to be able to learn it mathematically, automatically. And similarly, taking a look at a verse like this one's a bit more straightforward in terms of, what it means. But at the same time, even little things in the world of data science, like for example, the line gap, the line break between these two lines, sort of indicating a lyrical pause rather than a break in the sentence, right? These two lines are effectively one sentence that have been split into two because of the rhythm of the song, whereas these two lines have been split into two not because of a lyrical pause, but because they are completely separate sentences. You're starting a new sentence, right? Understanding all of these things can be really, really difficult. And you don't notice half of these problems as a human is the issue, right? And then, of course, there's also the problem that at the end of the day, it's art. It's up for interpretation, right? Like this specific line might not necessarily make any sense if you were to analyze it symbolically. You can't see things with your hands, right? That might look like a contradiction, but in the world of art, it works, right? This can be totally valid as a song lyric. And so I set out to build this deep learning based pipeline to generate music lyrics and help artists. And I'm glad to say that I was able to work with two sets of artists to put together some example music with lyrics actually written by the Lyricist system. And I'd love to go ahead and give you all a quick listen to a short snippet of a song called A Summertime Song by Claudia Heuser, a country musician from the States. And I'd love to go ahead and once again give you a quick listen to a clip of this song, and I'll also post a link where you can go ahead and listen to the full thing. Once again, lyrics partially written by the Lyricist system. Let's take a listen.
Replay it over all our favorite lines. It was never my intention to unwind. Loving you is like a summertime song. Cause it plays in past, daydreaming a feeling I can't get back. Oh, a summertime song. It's never my intention to waste your time. We jumped in the deep end and I lost what I was hoping to find. Replay it over all our favorite lines. It was never my intention to say goodbye. Loving you is like a summertime song.
It still fascinates me listening to this now that a neural network that I built wrote a lot of those song lyrics, right? It still, absolutely fascinates me that that was the case, that you can reach that level of quality when you work with human creative professionals instead of trying to replace them, right? I mean, you take a look at other projects like OpenAI's Jukebox, and you notice that a lot of their generations are kind of nonsensical. It's because these machine learning algorithms aren't optimized for generating sensical text, right? They're optimized very inefficiently. I'll get into that in just a moment. But when you work with human creative professionals on the task, you can achieve really high quality and help them in their process of getting across their message. Speaking of which, I would like for all of you to also take a quick listen to some of Claudia's thoughts as she was using the system, as well as her initial thoughts before she started using it too.
When I was first approached about this, I immediately thought, no way. When we're writing songs, I really try so hard to pull from my own experiences of people in the room, and just try to be as honest as possible. So thinking about a computer coming up with these ideas for me, I wasn't really having it, but I'm always up for trying something new. And what I realized was it was almost like working with an open-minded co-writer who just brought all these ideas to the table. And yeah, you could sift through the ones that were crazy and not going to work for you, but it kind of allowed us to think a little differently and took one of these songs that we had started in a completely different direction. So we were able to come up and find the line, "Loving You is like a summertime song," and now we have a brand new song that I just love. Hope you enjoy it.
That's the story behind how Claudia started working with the system. And, once again, I sort of love that sort of transformation from, being hesitant at first to then actually working with it and being like, hey, this is actually pretty fun tool to use. Help actually genuinely does help with the process. I absolutely love that. Now, getting a little bit deeper into the technology and actually building some AI systems. I believe that when you're working on building technology, it's really important to have the right mindset with it, sort of understanding its capabilities and where it can be applied. And for example, with the auto lyricist system, right? What sort of was the breaking point for me to actually work on building it was precisely seeing these different, for example, news articles online talking about AI replacing, creative professionals. And one of the sort of driving forces behind a lot of that hype was OpenAI's new technology. You may have heard of it. OpenAI recently, or this was actually some time ago now, they released GPT-3 to the public to use through an API. GPT-3 is a really large language model that can generate text automatically, reasonably, sensical text automatically. And that was accessible to everybody if they were to, pay for the API. And the thing about this technology is that while it does seem pretty capable, and while it can, generally generate a couple of sentences that seem pretty, that seem to sort of, follow reasoning rules and certain structures, over the long term, these language models aren't genuinely intelligent. They can't actually reason, right? There's no real human-like intelligence going on there, but that's not going to stop a bunch of different people from making it seem that way, because guess what? It's really easy to get a lot of people to click on your article if you tell them that AI is a lot more complicated or really intelligent compared to what it actually is, right? So for example, you take a look at The Guardian, even The Guardian, having GPT-3 generate tons of different articles and then manually, using their human editors to take individual snippets of all of them and sort of cherry pick and edit them together into an article and saying that a robot wrote the article, even down to the wording of a robot wrote this article, it's really misleading. People don't really understand what this technology is capable of. And I think that's an issue. However, that's not to say that it's not capable, right? So going back to the quote that I gave you at the beginning of today's talk about why machine learning is so disruptive, this quote, getting to who actually said this, it wasn't a human quote, right? This was actually generated by GPT-3 when I asked it the question, why is machine learning such a disruptive technology, right? So GPT-3 did not plagiarize this. This is not a quote that you can just see anywhere else online, but the point is, GPT-3 is not creative in what it says, only how it says it, right? GPT-3 is not reasoning, it did not deduce this, right? GPT-3 is effectively regurgitating what we've all been saying, but in slightly different ways because we randomly sample its output probability distribution. That's all there is to it, right? And the way that sort of the way that we came to this conclusion to use language models for understanding natural language this way is actually pretty interesting because, for example, with our brains, right, we could take a look at a sentence like colorless green ideas sleep furiously, and we pretty much instantaneously know that it doesn't really mean anything. But if it did, we'd be able to come up with all sorts of different interpretations, once again, practically instantly. But because of the complexity of our brains and the sheer scale of the way that they work, we can't just extract one, really well optimized sort of embedding or representation of that sentence from our brains. It's really hard for us to mathematically quantify what a sentence means. If anything, we basically can't do it. And so we try to use deep learning to simulate that ability within machines. And this brings me finally to how deep learning actually works and why we would come to the conclusion to use deep learning to try and simulate that ability, right? How to try and use deep learning to mathematically quantify the kinds of meaning in natural language and to potentially be able to generate it. Now, I think a wonderful little GIF to help describe how deep learning works is this one, a classic GIF about the joke that topologists can't tell the difference between a coffee cup and a donut. And of course, it's because they both only have a single hole, right? So technically they share the same topology. Now, why is this even remotely relevant, you may ask? Well, imagine you took this coffee mug, all right? And let's just say you took a blue and a red marker and you drew a bunch of dots all over it, right? In completely random locations. If I were to ask you to draw a single straight line in that space on the coffee mug that could separate between all the blue dots and the red dots, because they're all in random locations, there's a very good chance you can't do it. You can't draw a single straight line that separates all the dots. What does that mean? That means that the data is not what we call linearly separable, right? You can't separate it with a single line. However, imagine this. What if you could take the space that those dots were located on, and you could warp and twist and you could change the space itself such that after the transformation of the space, all those dots are in individual isolated clusters, and in this new space, you can draw a single line. I know that sounds weird, but that is exactly what deep learning does, right? It takes data that exists in some space, might be really high in terms of the number of dimensions, and it warps the space over and over again until we eventually end up with a new space where this data is projected in such a way that we can very easily delineate between different kinds of data within that space, right? So for example, taking a look at data like this, it's mostly linearly separable, right? There's three different categories, three different colors in this case. And if you were to draw two different lines, I can imagine red would be very, very easy to separate. And then with blue and green, you might get like two misclassifications, right? So it's mostly linearly separable. But this is not what the data looked like originally. Originally, the data looked like the data on the left, right? So green and blue were a lot more, mixed up with each other. And that's a problem, right? If you wanted to determine mathematically some sort of formula to determine whether a point in this space would be green or blue, you couldn't really do it accurately, right? You'd have tons of misclassifications. And so what the point of deep learning is we basically put together a really large, really complex mathematical function with a bunch of tunable parameters, right? And we use a bunch of calculus to optimize those tunable parameters such that towards the end of this neural network, this mathematical function, we're able to determine the difference between red, green, blue, the three different categories. Now, effectively, that ends up basically asking the question of, hey, how can we project this data into a space where it's linearly separable and then classify it, right? But there's no mathematical separation between, hey, let's make this linearly separable and then let's classify. What we're doing is we're taking one big black box function where data goes in, output is your predictions, and we're optimizing the parameters such that we get better predictions. And what ends up happening is because of this just being the simplest way to do so, you will converge to a set of parameters through your optimization that help you linearly separate your data, right? That I think that is a very interesting mathematical property of the way that deep learning systems work. And I want to go ahead and just quickly show you what I mean by that through a demo called the Tensorflow Playground. This is something you can spin up yourself. You could Google Tensorflow Playground right now, start playing around with it. And basically, the Tensorflow Playground is a project by Google, helps you mess around with the deep learning algorithms in your browser. On the left, you see your input data. On the right, you see your output data, right? So for example, in this two-dimensional space, when you've got dots in this cluster, you want them to be classified as blue. And when you've got dots in this cluster, you want them to be classified as orange, right? So pretty simple task for the neural network. Basically, you want these dots to sort of output -1, these dots to output +1, and you can see your X and Y values over here as well in the space, right? So as a human, super simple for you to do so. One of the ways that you could do this would be to simply take the X value on the graph, right? So if I hover over this, you can see the X values, reaches -infinity here, +infinity that way. And of course, in the middle, 0. So if I hover over this, you can see that delineation. Is if I were to just click on this, this is sort of input to our network now. And all our network is doing, right? It's not complicated at all, is we're doing a single multiplication. That's it. We take our input X value, we multiply it by what's called a weight, in this case, -0.13, and the output of that multiplication is our prediction for whether the dot is blue or orange. As you can see, it's not a good prediction, but if I click this play button, we'll actually start to use that same calculus, the gradient descent, to optimize that weight. And now if I go ahead and run that, as you can see, we have our predictions being made over here, right? So the background of the space is the predictions we're making from our neural network, if you want to call it that, even though it's really tiny. And as you can see, we can determine what space is blue, what space is orange very accurately, right? Super simple task. If we take a look at our weight, it's 0.91, which makes sense intuitively, right? Now, what if we wanted to come up with a better line, right? Like, for example, this line is just a straight line. What if we wanted to make a diagonal, right? Because, as a human, you would probably I would at least draw a diagonal between these two clusters because of their positioning. Well, we're currently not feeding enough information into this network for it to do so. All it knows is the X coordinate. It doesn't know the Y. It can't draw a diagonal line. So if we were to also feed in the Y position of each dot, now suddenly our neural network can draw more complicated lines, right? So what we're effectively doing now is we're taking the X and the Y, we're multiplying them by their own individual weights and then summing them. We're getting a weighted sum of our inputs, in this case, the X and the Y coordinates, and that would be our output. So if I click on play, I optimize. As you can see, we converge to a set of weights that help us more accurately delineate between the blue and the orange dots. Pretty nice. Now, of course, we can get a lot more complicated. So for example, let's just say we're dealing with this data set over here, right? So we've got a bunch of orange and blue, but in these sort of like quadrants, right? How do you want to separate between these? Well, if I were just feeding in the X and the Y coordinates, as you can see, our neural network is not having a good time because of two reasons, right? First of all, there's very little data to work with. Theoretically, you could just use the X and the Y to figure this out, but it would be very complicated. And also because there's not enough compute capacity, right? There's not enough space for the neural network to learn, because all we're doing is we're getting a weighted sum of the X and the Y, right? So what we can do is sort of introduce the magic of deep learning, which is hidden layers, right? So what we do is we introduce this sort of layer where what we do is we get the weighted sum of the X and the Y, and then we take that and we get another weighted sum, in this case of just a single value, and then that's our output instead, right? So we introduce this extra layer of nodes in between that can make these as many as we want. Like, for example, now we would get 3 different weighted sums of our X and Y, isolated weighted sums of our X and Y. And then we would take those 3 values, get a weighted sum of them, and then that would be our output, right? So if I click play, we might have a slightly better time trying to figure out weights, because now we can draw even more complicated lines. Right now, we have these 2 lines over here to help us delineate between blue and orange. Now, it's still not perfect, right? Ideally, we would have orange over here, and then blue here and here. And so how do we achieve that? Well, there's a couple different ways, right? One of them is we could add another hidden layer, right? And we could create even more internal connections for this neural network to optimize. And what this is doing is, once again, it's increasing the complexity of the lines that we can draw in this space, how we can actually warp it to be able to separate. As you can see, we're approximating something closer to what I originally wanted, but we can make the task way easier for the neural network. How do we do it? Well, if we were to feed in X times Y, which naturally looks like the data distribution that we have in the output, now if we were to feed this as an extra input parameter and click play, suddenly the neural network has a lot better information to work with, and we practically instantly converge to a wonderful solution, right? So this is, just a small glimpse into the way that these networks work, right? Again, what's basically happening here is we're saying, these are our input features. We want to get a few different weighted sums of those inputs, and then take those, get another weighted sum, or multiple weighted sums, and then final weighted sum is our output. What I think is really fascinating to see is how these weights actually change through the process of gradient descent. At first, all these weights were reasonably the same, but X times Y is such an incredible input for predicting this, that if you take a look at the weights for the X and the Y parameters on their own, they're very close to zero, right? The neural network really does not care about these values. It almost zeroes them out, but it really cares about the values from X times Y, because it is, once again, very close to the output distribution that we want to get. And so it's fascinating to see how these neural networks learn. But because this is a very small network, we can pretty easily sort of zoom in here and be like, hey, there's a pattern in how it learned. But as you get much larger neural networks, it can be very hard to do that, right? Like, for example, I actually have a quick demo I'd like to show you before I sort of jump over into a Q&A. Well, actually, no, we do have enough time for me to sort of cover one more thing here as well. And that is an example in the visual world, right? How you understand images. Of course, visual recognition is a sort of classic use case for the world of machine learning. And what I sort of described in the way of making data linearly separable applies almost the same way to that world, right? So for example, if you were to try and classify between cats and dogs, classic machine learning example, then you would be feeding your image into traditionally what would be a convolutional neural network. That convolutional neural network would then feed into a similar, neural network like this one, where you calculate weighted sums. We call that a linear layer. And then that final layer would output your probability distribution, right? What's the probability that you have a cat? What's the probability that you have a dog? And if you take a look at sort of the way this works, you can think about all the pixels for the cat representing a very large multi-thousand dimensional input space that's very complex, right? Points in this space are very difficult to decipher because they're not linearly separable. If you had a bunch of pictures of cats and dogs and you represented their pixels as coordinates in this space, you're not going to be able to draw a single straight line between them. But through the transformations of the convolutional neural network, we end up creating an embedding of the cat that is now linearly separable, and that we then separate with a linear layer in order to figure out the class probabilities, right? That's what we have. And in order to do this, we have our training objective, right? So as I mentioned, this is all one black box. We're not over here mathematically formulating how to tell a convolutional neural network to linearly separate cats from dogs. Instead, all we're doing is we're saying, all right, here's a very, very large mathematical function with 300 million inputs, right? And these are all parameters that are tuned by gradient descent. And in goes an image of a cat, out comes a probability distribution. Can we optimize these parameters that are being fed into this function? And the way we optimize is through the training objective. In this case, the training objective is, can we classify between cats and dogs more accurately? But you could have all kinds of training objectives, right? We could, for example, instead of specifically saying, here's a cat and here's a dog, we could take 3 images at once. We could have 2 of the same category and 1 of a separate category. And instead, we could have multiple different outputs that represent a point in, say, 10-dimensional space, right? And we could make it so that the points for the cats are closer and the point for the cat and the dog are further away, right? And so now suddenly we're still being able to linearly separate between the cats and the dogs in an arbitrarily high dimensional space. But now we're doing so in such a way that we never need to explicitly say, here's a cat and here's a dog. Instead, we say, here's 3 images. These 2 are similar. These 2 are dissimilar, right? And we end up learning a sort of similar representation internally by doing so. And the training objective is really, really important, right? Because once again, you have to realize that artificial intelligence doesn't learn the same way that we do, right? Natural intelligence, it does not work the same way at all. And what that means is that what they are capable of is very different from what you might think, right? So a friend of mine, Tim Duncan, actually wrote an article a long time ago, and I think it's a really fascinating article because it talks about how the US Grant Office created grants to incentivize the total number of arrests made by each police department in the states. And that was sort of an objective for them, right? Was to sort of increase the total number of arrests. And you know, there was sort of the sort of justification behind that, which was, you know, to be able to, for example, you know, ramp up the war on drugs. But then you end up realizing that humans are lazy and greedy. And what that means is that we will try and find the, you know, shortest possible way, the easiest possible way to achieve some kind of objective. Regardless of what the intention behind that objective was, we will find the easiest way to achieve that objective. And that leads to, well, this, right? And so what we want to do is we want to come up with objectives for humans, of course, that make it so that the easiest way to achieve the objective is your intention behind why you set the objective, which is a really difficult task to do, right? It's really hard to engineer objectives like that. And it's also equally hard to A, engineer mathematical objectives for neural networks this way, and then B, understand what those objectives are optimizing for, because we have the bias of human intelligence, right? At the end of the day, neural networks are just really, really large mathematical optimizers. And the problem is that the training objective isn't just telling the neural network how to learn, but how it learns also affects what it learns, right? There's a very big difference there. And it's something that a lot of people don't realize, right? Like OpenAI, for example, their GPT-3 solution for generating natural language cannot reason. It has no semblance of real human intelligence, even if it might look like it. And the reason for that is because the training objective is just, here's a bunch of words. What's the next word in the sequence, right? That training objective does not force the neural network to converge to a set of weights that would reason. Instead, it's just modeling a distribution of words. That's all it is, all there is to it. On short term, you know, on short scales, over a couple of words, it might look intelligent, but then you start generating a lot and you start to realize the limits of that training objective. It does good enough mathematically without reasoning that there's no need for it to find the better set of weights that would simulate what we might call a reasoning capability. As I mentioned, there was one more demo I'd like to show you around, you know, being able to understand visual data. And that's a really quick one here that I'd like to show you. It's a script that I put together, and this is something that I will give you a link to train a neural network called ResNet-50. So ResNet-50 is, well, I remember when they released a paper for this, you know, back in the day, but, you know, now it's a classic neural network architecture for visual recognition and understanding images. It's by Microsoft. And here's a little script. All this does is it loads in a bunch of data, cats and dogs in specific. And then once it loads that data in, it creates a ResNet-50 model, trains that model to be able to determine the difference between cats and dogs, and then saves that model to the disk, right? That's really all this model does. It reaches about 95% accuracy very quickly. And this is on an M1 Max, so on Apple Silicon, you know, quite literally on an integrated GPU. We're reaching 95% accuracy in, you know, 10 to 15 minutes. And what's really fascinating, and I think this is really interesting, is if you take the last bit of the neural network where it predicts, you know, is this a cat or is this a dog? And if you strip away that last layer and you take a look at the second last layer, right, the penultimate layer, Of course, this layer has a bunch of different nodes. Once again, it's a hidden layer. It has somewhere around 2048 individual weighted sums of the layer before it. And if you were to take that 2048 dimensional coordinate, essentially, and if you were to run dimensionality reduction and bring it down to just 3 dimensions, and if you were to plot what that data looks like in 3 dimensions for a bunch of different cat and dog images, I think you notice something really fascinating. You start to notice precisely the, as you can see, we're actually at 98.3% accuracy. But you noticed exactly the pattern that I was talking about a moment ago, where all the images are linearly separable, or at least mostly, right? If you take a look at the red being the cat, the blue being the dog, you start to notice that despite the enormous complexity of the input space of the images, we end up in a very simplistic space where we then just draw a line effectively, right? That's what deep learning is. It's really, really fancy ways of convincing computers to draw lines in arbitrary spaces, right? And how we do so is very complicated because, once again, there's just too many millions of individual parameters for us to understand what each parameter is doing. And so that's sort of the crux of what deep learning is all about. I think that's sort of like a sort of good mindset to sort of enter the world of deep learning with. And at the end of the day, one more thing that I do want to quickly say before we jump into a Q&A, because I'd love to answer any questions you might have, is that, I mean, technology has always been about solving problems, right? Solving humanity's problems. And that's something that I've always believed in. It's all about, augmenting human capabilities. And a lot of people will rush to say, hey, AI is really fun. We should apply it everywhere. But just keep in mind that at the end of the day, as a software engineer, as a computer scientist, as a machine learning engineer, really AI is just another tool in your tool belt, right? You can solve problems with all kinds of technology. And you should always start with the problem first and try and determine if AI or machine learning is a valid solution for this problem, instead of starting the other way around and saying, hey, AI is really fun, what can we do with it? I found that can have a lot more of an impact, and then you end up with way more fun projects. So that's sort of what I have to say about the world of AI. Now I'd love to go ahead and answer any questions you might have. Of course, feel free to reach out to me after this as well. The links I promised for the music video and the code that I've shown you, I'll go ahead and provide that with you, provide that to you in a moment. Yeah, I'd love to go ahead and answer your questions now. Since this is hybrid, I mean, if we have any questions from in person or like in the Zoom chat. Yep.
Do you guys have any questions here? Okay, yeah. So we have a question in Zoom. So how can we get started with AI and machine learning, neural networks? Are there any online resources?
Totally. There's a lot of different resources for learning this online, but I will say that a lot of them teach very differently. The few that I would recommend would be I mean, of course, there's my YouTube channel. I have a lot of different machine learning and deep learning tutorials on there, as well as a website called cognitiveclass.ai. They're a wonderful learning platform for all kinds of things. They have a course called Python for data science. Do take a look at that, as well as machine learning for beginners. So cognitiveclass.ai is a great resource to use, as well as Google has TensorFlow in specific has a lot of different tutorials on their YouTube channel of using TensorFlow specific, machine learning features. So I'd recommend those sorts of resources to start off with. That'll give you a really good primer and sort of get you up to speed. From there's more complicated stuff available on platforms like, for example, Coursera, that you can take a look at as well.
Yeah, there's also another good question by Michael. He's asking, do you think Julia will take over Python as the go-to machine learning language in the future?
It's a wonderful question. Here's the thing. Python has such a large community. They've been doing machine learning for so long now, right? Companies have been applying machine learning in Python for so long that it's really, really hard to uproot everything that we've done in Python and move over to another language, even if it would be better, just because there's millions of lines of legacy code and infrastructure already written in Python that people need to not only maintain, but also continue to support and improve. So I would say that in an ideal technical world, Julia should in the future take over Python. And just for context, everybody, Julia's the programming language, it's compiled. It sort of reads like Python, but runs like C, sort of their motto, right? You get really high performance out of what looks like a scripting language. And it has, really, nice built-in features for scientific computing, like, for example, with machine learning. So in an ideal world, it should be able to, but realistically, while I don't think it's going to take over Python in the near future, at least, it's going to be a really large player, right? Already a lot more companies use Julia than you might think. Apple, NASA, Google internally, quite a few teams use Julia for certain scientific computing, machine learning applications. So I would say it's really valuable to learn. It can help you build models better. It'll be great for your research. But in the real world, Python, I don't think we'll be able to dethrone it, at least for now. And also, if you're looking to learn Julia, I have a book called Tanmay Bakshi Julia that you can use to learn the Julia language, which I think is a great resource to get started.
Yeah, so there's another question about your project. So Jamin is asking, like, can you give a little overview of the project Lyricist, like specifically after the learning phase? What was your input to generate new lyrics?
Totally. Yeah, it was a really fun project to work on. Effectively, the input to the way that Lyricist was trained was actually quite complicated. There were a lot of different phases to training. On a high level, effectively, I'm showing it a lot of existing song lyrics, having it predict completions for those song lyrics. And then from there, also having two other neural networks predict the relevancy of lyrics to specific songs. So trying to predict, for example, if a generation actually makes sense, but then also trying to predict the quality of these generations was another separate isolated system. So there were sort of three components to it. At the end, once everything was done training, the way that it worked was this. You had, for example, an artist that would say, like Claudia, right? She wrote a bunch of sample verses or choruses that represented what she wanted the song to be about, or something, in terms of getting started, right? Like sort of like a seed to work off of. You feed those into the Lyricist system and say, I want a bunch of verses, or I want a bunch of bridges or choruses or whatever. And Lyricist will come back to you with basically an infinite scroller of a bunch of different sections, really whatever section you asked for. Now, what's interesting about the way that this works is that it's not just generating content like something like GPT-3 would, it's also analyzing the content that it generates with respect to what you fed in to give you generations that are both high quality, but also relevant to your input, right? And so it sort of becomes a collaborative process with the machine at that point, where you start with something, or you could even start with nothing, just have it generate from blanks. But you could start with something, have it generate based off of what you gave it, and then use that to sort of improve your messaging, get more of your stuff across, sort of feed it back into Lyricist, get more output, and sort of work with the machine in that way. So that's sort of what you would feed in, what you would get out. And I think it's a really fun sort of collaborative process once you start working with it.
Got it. Thanks for sharing the insight. I had a question just to build on it. So for the Lyrics project, like, you said that we need to have like a good objective function for the deep learning neural networks. So How did you define the objective function for this project?
Totally. So there were a couple different objective functions, because once again, there's multiple different deep learning pieces to it, as well as a pretty experimental one that I'm actually still working on right now. But there's sort of three ones. One that was a very classic language modeling objective. And so the idea is that, hey, given a bunch of lyrics, can you predict the next lyrics? And it's sort of just a token per token loss function, where we're saying, for every token that you predict, was it correct, compared to all the tokens that came before it. So there's a classic language modeling objective, but then there's also two more objectives. One of the objectives is to take an arbitrary section of a song and predict if it was human written or machine written. The reason this objective function is nice is because then it helps me train neural networks that can do quality estimation to see if something sounds machine written or sounds human written, right? The ones that are human written, I assume to be higher quality. And then finally, there's also another objective function where I take three different sections of songs, two of them from the same song, another one from a different song. The way that these are sampled has to be very special to make sure that we don't get very similar sections of songs. But effectively, I learn another neural network to embed different sections of songs closer together in a space versus sections from separate songs. That helps me then predict relevancy to say, hey, if the neural network generated something, can we predict if it's actually relevant to the seed that the artist fed us with? Right. So that's sort of what I use it for. And I'm also working on an experimental reinforcement learning objective to help the neural network sort of just improve on its own generations based off of human feedback instead of a specific, per token, is this correct or is this incorrect marking. So still working on it, but I think that would be a fun objective once I get it to work. Expensive though, I will say.
Got it. And did you use any specific n-gram model, like bigrams or unigrams, to build the neural network? How did
that is a part of the data sampling for relevancy prediction, because as I mentioned, we don't want to collect two sections that are really similar because they're going to have similar embeddings anyway. We want to get the most dissimilar sections of a song and then force the neural network to think that they're similar based off of the context, right? And so that uses some bi and trigram modeling in order to make sure that we get dissimilar sections.
Got it. Yeah. Thank you so much for the information. Okay. Are there any more questions in the chat? You can just speak out if you want, or type it. Or any questions here? Any general or specific questions? Okay. Let's see. Any questions in the chat? Okay. So how can they connect with you, and we can get the links that you just shared with us, the code links?
Totally. I'll go ahead and should I send those to you, and can you post them along with the recording of the video?
Yeah, sure. Yeah. If you can add some links in the Zoom too, and just share with me, because some people are not outside of the GDSC.
Right. Yeah, right. That makes sense. I will go ahead and send those to you in the Zoom chat now.
And yeah, if any of you are not on our Discord, try joining that, and I can post up those links on the Discord just for you to access it. Let me share the link tree. So this is the link tree. You can join the Discord. I'll share the resources and also the recording of the video if you want to play back and check some parts of the videos again. Okay.
Wonderful. And I have put the link to the song as well as the GitHub gist for the code in the Zoom chat.
Got it. And okay, so there's another question by Jamin. How do you see AI in political decision making?
Okay, that's a really good question. I would say machine learning helps you. I mean, as I mentioned, right? The point of AI machine learning is to help with pattern recognition at the end of the day, right? And machine learning isn't creative. And I feel like political decision making is the kind of decision making that requires a lot of creativity, right? It requires a lot of what hasn't been done before. What can we do that's new based off of what has been done before, right? Reasoning, almost. There's a lot of reasoning that's required in political decision making, and AI can't do that today. Right. And so I see AI in political decision making the same way I see it in, for example, law, right? It's helping us take a look at previous precedent, big data sets that we might have, being able to find not just patterns, but also specific instances, being able to pull up data more effectively to help us make decisions, right? I think that's sort of the main role for AI, because we don't currently have a good way of combining symbolic and neural reasoning with the AI systems. Eventually, once we do, I can imagine it would actually help us make more concrete decisions. But as of right now, I feel like it's more going to be used as a resource for humans to pull up the right information with which to make decisions right now.
Yeah. Also, don't you think there may be issues in the accuracy of the suggestions? Because if someone builds the models, there's bias involved in it by humans themselves. Right. So different governments may have different biases for their own AI models.
Right. Yeah, that's a big concern. Definitely is. We already live in a world of technology where your own opinions are consistently basically thrown back at you because a lot of these systems are trying to optimize for example, for you to stay on an app for as long as possible. And the easiest way to do that is to show you things that you'll probably agree with.
Yeah.
But I mean, at the same time, there are ways, to take a look at the way that these models work, and try and minimize, human bias from these models. At the end of the day, once again, the objective function is optimizing neural networks on the data you feed in, and this data is bound to have human bias. But there are ways to help them, probe those models, figure out why they make decisions, at least at some level, and help, somewhat remove bias. So that's something that's still a very active field of research. But I think it would be interesting to see, the way that we could potentially, use this technology to sort of more objectively analyze the way that we make decisions. I think that would be an interesting future.
Got it. And then just for beginners, like if they want to get started in machine learning or deep learning, like should they focus more on like the math aspect of it, or should they just focus more on the application aspect of machine learning to just get started?
So I'm going to use the analogy of something else really quickly to answer this question. I mean, I personally, for example, the way that I learned how to code, right, was very organic in the sense of, I used very few like actual resources like books or courses or whatever to learn. I sort of just did it over the course of a couple of years. And like, for example, I never really formally at first really learned, like, for example, big O notation. I was never like, these nested for loops are n squared, right? Like when I was 7, I was just like, hey, 2 for loops slow. How can we make faster, right? That's sort of at the end of the day what the decision making was. I sort of learned these things organically. I think it's very nice to learn things organically, but it's also kind of impractical because that just takes a really long time. You got to build a lot of things. You got to make a lot of mistakes. You got to learn. I've had the advantage of being able to do that since I was like 7. So that organic learning kind of just worked for me because I've been doing it for a long time and I love doing it. While that is what I like, I can't necessarily recommend it. Similarly with machine learning, it's optimal to be able to start with just a bunch of applications, right? Think what would be something that's fun to do that we could do with machine learning and just start building things. Use the Watson APIs, use the GCP, AI capabilities. Use these different APIs to help you build applications, get a good sense of what machine learning can do, and then sort of slowly dig deeper into individual things and say, hey, I use that API. How does that work? Could I make my own model that does that, right? And that's sort of how I did machine learning as well, right? Since, once again, I've had the advantage of doing it since I was 11. But realistically, I would say you need a good balance of it. Start off with, some of the more fundamental, math. I think that's good to help you build an intuition just right off the bat for what these models can and can't do. Once again, as I mentioned, a good way of doing that would be to take a look at resources like Machine Learning for Beginners on cognitiveclass.ai, and other resources like my YouTube channel, my Deep Learning from Scratch series. But then also at the same time, make sure you really do focus on the applications and you don't get too bogged down by the math too, right? Make sure you actually compete in Kaggle challenges. Take a look at random open source projects that you think are fun, right? Like I remember a little while ago, I was just randomly taking a look at an application by, I forget the university, but it's background matting, right? So like predicting green screens to be able to blur out pictures. It works wonderfully well, right? Like you could be, waving your hair around and it would almost perfectly segment all of your hair from the background. It's pretty amazing, right? So just take a look at random open source projects, try to build things yourself, get other people's open source projects to work on your own. That's a big one. You'd be surprised how much you can learn just by running other people's code. I think that's a good way. Experiment, but also take a look at the fundamentals so you're not, spending a couple of years just messing around before you figure things out. So a good balance.
Got it. Yep. So are there any questions in the chat? Let's see. Okay. So if they want to like connect with you, should they like send you emails or like through LinkedIn?
Absolutely. I will show you once again. So just sort of, I'll share my screen really quickly. If you'd like to connect, feel free to do so on any of the following platforms here. I'd be glad to get in touch. Feel free to send me an email or send me like a DM on LinkedIn or Twitter. Pretty much anything works for me, and I'd be happy to answer any more questions or get in touch.
Got it. And if they want to like join you through LinkedIn, should they add some note that hey, I attended the event today.
Sure thing. Yeah, just let me know you saw the talk at for the GDSC UMN, and I'd be happy to connect. And speaking of which, if you're also on the GDSC Discord, feel free to connect with me. I'm not sure if I'm on it, but if I'm not, then I'll join in. Then yeah, feel free to connect with me there too.
Yeah, that would be really great. Yeah,
Totally.
and yeah, thank you so much for this amazing talk. I really enjoyed to like learn about the projects and how you
Thank
like
you.
bust some of the myths about AI and how people just sensationalize stuff about it. So it's important to like give the right perspectives about it and how what are its practical capabilities and how we should not over exaggerate, but also not
Right.
underplay the consequences of it.
Precisely.
Thank you so
Thank
much
you.
for joining. Thank you everyone for joining us. I hope you guys learned a lot and you guys can surely connect with him. And yeah, I'll post the links on the Discord. Thank you so much.
Sounds good. Thank you very much.
Bye guys.
Bye.
Let's go.